And now let's look at our first two clustering algorithms, kMeans and kMedoids. kMeans and kMedoids are very similar, except that kMeans works based on the computed centroid of a cluster, whereas kMedoids works based off of the data point that is closest to the computed centroid of a cluster. But K already tells us that we are going to have to supply to the algorithm a number. That number, K, is the number of clusters that we want our algorithm to discover. Here is how kMeans works. At the outset, our algorithm partitions our data space into K, the number that we supply, partitions, and then drops a K number of centroids randomly into those partitions. It then looks at all the data points around those random centroids and computes the distance to this centroid. If a point is closer to one centroid than to another centroid, that point is being assigned to our first cluster. If a point is closer to another centroid that has been randomly dropped into the data set, then that point is assigned to the other cluster, and so on. Once all data points have been assigned to clusters during this first iteration, our algorithm looks at the cluster and recomputes the centroid so that the centroid will be in the middle of the cluster for the data points that have been identified in this iteration. Then we go into the next iteration. And the same thing happens again, namely our algorithm goes out, looks at the recomputed centroid now, and looks at all of the data points that could possibly be close to this recomputed centroid. It assigns again the data points to the closest centroid, and then when that iteration is done, recomputes the optimal location of the centroid. During the next iteration, the same thing happens again, and during the next iteration, the same thing happens again. We are done with iterations when the centroid location does not change anymore. Here's what this looks like. In our iteration 1, we see our random partitioning of our objects here into 3 spaces. Our K that we have set here is obviously 3. We also see 3 randomly allocated centroids. We're seeing that our first centroid in the green space here obviously is off to the side because the green space down here needs a centroid that is closer. We're seeing that the same thing holds true for our blue data space here, in which the blue centroid is much too high. So during our second iteration, we're seeing that the green centroid has moved more into the middle of the green data space. The blue centroid has moved more into the middle of the blue data space. This leaves points at the top here, the top area, closer to the red centroid. So all of these points that were previously blue in our first iteration are now red because they have been reassigned to the red cluster. Of course, that also means that we need to recompute the centroid of the red cluster because it is now also too high, and that's what happens in iteration number 3. In iteration number 3, this centroid has moved more to the middle of the red cluster, but that also means that we have data points that have now to be assigned from the green cluster to the red cluster because they are closer to the red centroid now than they are to the green centroid, which has moved more into the middle in order to be closer to the data points at the bottom here. And the same thing holds true also for the centroid of the blue cluster, as we're seeing here. This area, some of these data points have been assigned to the red cluster. Iteration 4 does exactly the same thing, namely relocate the centroid of the red cluster and relocate the centroids of the green and the blue clusters respectively, until In iteration 6, we have achieved the optimal location for our centroids in the middle of each cluster, and we have identified the best separation, the best partition among our 3 clusters that gives us a high intra-cluster similarity, meaning very short distances between our centroids and our cluster points, and that gives us an optimal inter-cluster distance, meaning a greatest distance between our cluster points here. So k-means looks for clean partitions, in other words. This also means that it does have limitations when it comes to clusters that have different densities, and when it comes to clusters that have different shapes. Since, as we can see here in this example, k-means really looks for clean partitions, it is kind of hard for it to recognize density-based shapes. This is what we need other algorithms for. Another weakness of k-means, honestly, is that we need to normalize all of our values before we start running k-means, because we are working with distances. Obviously, that means that we can work only with numeric variables. And since one of our hallmarks for a desired quality of a clustering mechanism was that it can work with all sorts of different attributes, that really isn't quite true for k-means. So for categorical data, there is a kModes method. kMedoids can help us get over some of the limitations of k-means. kMedoids, or partitioning around medoids, PAM, then does not start from a centroid and computes the distance from a centroid, that is, from an artificial center of a cluster, but it starts with a data point that's as close to the centroid as possible. Here the slide says a centrally located data point or object. And from there, from an actual data point, then builds the cluster. So in our data space here, we're seeing 2 clusters. We're seeing a light blue and a dark blue cluster. And we're seeing that for the light blue cluster, our centroid is probably somewhere around here. And for our dark blue cluster, our centroid would probably be somewhere around here. Now, our closest actual data points to a calculated centroid are this one here in our light blue data space and this one in our dark blue data space. And this is what kMedoids does, namely it takes the actual data points that are the closest to the calculated centroid and marks these as the middle of the cluster. That's what we're seeing on the right side of this graphic. So kMedoids operates in a very similar fashion to k-means. But where in k-means random centroids are being deployed, in kMedoids an arbitrary object is being chosen in the data space as the initial medoid. And then all the remaining objects are being assigned to the nearest medoids instead of the centroids. And then we are computing the distance from each medoid to the assigned objects to ensure that the medoid is in the correct position. If it is not in the correct position, it needs to be relocated. So then we compute what is called the total cost of swapping, meaning that our initial medoid object is going to be unmedoided, and another object that is close to it will be picked as the new medoid and as the new middle of our new cluster, and our process loops until all the medoids have been optimally identified in our K clusters. So what does this look like in R? Well, first I'm going to install the cluster and the FPC packages because I'm going to need those. And then, because I'm going to work on my iris dataset, I'm going to back up my iris dataset into iris2 because I'm working with clustering, which means that I need a data frame that does not contain the class attribute. And we know that the class attribute is species. that has these 3 species in it, and that my other 4 attribute, namely petal length, petal width, sepal length, and sepal width, are used in order to assign a tuple in my data set to that class. However, if I delete the class attribute, then I can test whether my clustering algorithm correctly recognizes these 3 categories based on just the measurements of the 4 input attributes. And that's what I'm going to do now. So first I'm going to make my iris2 dataset, and then I'm going to delete my species attribute. So now I can run my kMeans algorithm on my iris2 dataset, which does not have the species here anymore. And I can tell it to find me 3 clusters because, as I said before, we're going to cheat. We know that there's supposed to be 3 clusters, right? So we're going to do that. And then I'm going to compare my result that I've achieved in my k-means analysis to my actual species assignments. That way I can test whether my k-means algorithm was successful or not. So I'm setting up a confusion matrix here. Across, I'm seeing my cluster assignments. Down, I'm seeing my actual class labels. So I can see that for setosa, all 50 setosas have been assigned to cluster number 2. That means that setosa is very easily recognizable. For versicolor, I'm seeing that 48 of my 50 have been assigned to cluster number 1, and 2 have been assigned to cluster number 3. So versicolor is still also kind of pretty well recognizable based on the 4 input attributes. The story is quite different with Virginica. In Virginica, I'm seeing that 14 of my Virginicas, based on the measurements in their 4 input attributes, have been assigned to cluster number 1. That's the same cluster that also contains my 48 versicolors. And I can see that 36 of my Virginicas have been assigned to cluster number 3, in which I'm also finding 2 of my versicolors. So while that's only a small overlap here, we can already see that it's harder to differentiate between versicolor and Virginica than it is to differentiate between these 2 and setosa. Now let's plot my clusters. I'm going to use just sepal length and sepal width here, and I'm going to assign the points for my centroids to sepal length and sepal width as well. So here are my clusters. As we can see, based on sepal width and sepal length, we can see here is my Virginica and my versicolor. This here is quite obviously my setosa. So let us set our centroids and look at this again. And yes, so this is what we're seeing here. Well, let's see if we're luckier with our K-medoids approach. We're using the FPC library, and we're going to apply our PAM-K algorithm to our iris2 dataset without, in fact, giving it the number of clusters that we want it to discover, but we're letting our PAM-K algorithm discover its own clusters. So for that, we're going to take a look at the number of clusters within PAM-K, and we're seeing that PAM-K has discovered not the 3 clusters that we want it to discover, because we know that we have 3 species, but PAM-K tells us there's only 2. Now let's see. Let's check the clusters against the actual species here. So I'm going to from my PAM-K result, look at my objects here and at the clustering space, and then I'm going to look at my original iris data set and at my species assignation. And then I'm going to lay that out into a matrix with 2 graphs per page. I'm going to plot this, and then we will see what the results tell us. So here we're seeing Setosa has all been assigned to cluster number 1. And we're seeing cluster number 2 contains almost all of versicolor and certainly all of virginica, and one little versicolor here made it into cluster number 1. That kind of confirms what we've seen with kMeans with our 3 clusters, because here we had a very clear assignation of Setosa to 1 cluster. And we had a mix of versicolor and virginica in 2 clusters, and that's also what we're seeing right here on our graph. And now PAM-K tells us that there really should be only 2 clusters, one being Setosa, pretty much all of it, and one being versicolor and virginica mixed. So let's plot that. And what we're seeing here in our cluster plot is this. We're seeing our Setosa right here, and we're seeing our virginica and our versicolor right over here. Here we are seeing the intra-cluster distance, and we're also seeing in our analysis that our 2 components here that have been artificially built explain 95.81 of the point variability. Now, we can look at our data space like this, or we can look at our data space through a silhouette plot. And in our silhouette plot, we're seeing a clear separation right here in this white space between cluster number 1 that contains 51 data points, the 51 being our Setosa and our versicolor, and our cluster number 2, which contains 99 data points, namely our versicolor and our virginica right here. Well, we let PAM-K pick its own number of clusters. What if we run our kMedoids approach and we force our algorithm to recognize 3 clusters, because we are still not giving up on our 3 different classes, right? So we're going to, for that, use the cluster library, and instead of PAM-K, we use our regular PAM partitioning around kMedoids approach on the iris2 dataset, and here we give it our K equaling 3. We're going to stick that into PAM result, and we're building our confusion matrix again here. And we're seeing we have our 3 clusters here. We have our Setosa, versicolor, and virginica, and Setosa is clearly assigned to 1 cluster, and we have a mixed cluster here between versicolor and virginica, which is pretty much the same that we had here with 48 and 14 in our kMeans. And we have a 3rd mixed cluster between versicolor and virginica of 2 and 36, which is pretty much exactly our output of our kMeans as well. So now let's plot this and see what our result looks like. I'm going to again set my layout to display 2 graphs per page, and then I'm going to plot the result. And we're seeing here in my clustering plot that our Setosa is very well defined, and that we have our 2 overlapping clusters of versicolor and virginica. It's quite obvious here. And we're also seeing the inter-cluster distances marked by the magenta lines here. Our silhouette plot then identifies our cluster number 1 with the 50 elements here. And we're seeing that this is this cluster number 1. And then shows us how our cluster number 2 and number 3 with 62 and 38 elements here basically overlap. But I'm sure you now have a huge question. What if we don't know K? With our iris dataset, we basically cheated. We already knew that we were looking for 3 clusters because we knew the contents of our species attribute. What if we don't have that class attribute? What should we pick as the optimal number for K? This is where the elbow method comes in. The elbow method is the most popular method to determine the optimal number of clusters in a data set. Here in our example in Python, we're first creating our data arrays and then we're plotting them. And in our plot, it looks like, yeah, there probably could be 3 clusters. But trust and verify, right? There are 2 mathematical factors that we can use to our advantage to calculate the optimal number of K. First is distortion. Distortion is the average of the squared distances from the cluster centers of our clusters. And the other one is inertia, which is the sum of squared distances of the samples to their closest cluster center. So first we're going to build our clustering model, and then we're going to calculate the values of distortion and inertia. Here we are building our kMeans model on our n clusters. That is going to be K, and we're going to fit that to our X. So our kMean model is going to be fit to our X. And then we're going to calculate our distortions. As you can see, calculating our distortions is a little bit more involved than calculating our inertias. We can, in fact, pull our inertias directly out of our k-mean model. We have to calculate our distortions. So for that, we're going to calculate the sum of the averages of all the distances from the cluster centers, and we're going to use the Euclidean distance for that. Then we're going to create 2 mappings. One for our distortions, that's mapping 1, and mapping 2 is for our inertias. And now for each K from 1 through 9, we're going to print our distortions, and we're going to print our inertias. Then we're going to plot our distortions, and we're going to plot our inertias. And ideally, both will have the same outcome, as they do here. What are we looking for on the elbow plot? On the elbow plot, we are looking for the elbow that is the number after which our line looks almost linear. And that in both cases here is 3. So just for fun, we're going to take a look at our data set here with 1, 2, 3, and 4 clusters. And we're seeing that with 1 cluster, well, that's the whole data set. With 2 clusters, we're seeing, oh, okay, so there's the first cluster that we're identifying is this down here. That kind of makes sense if we just kind of, visualize it. And our 3 clusters correctly identify what we had in mind. And if we pick 4 clusters, that seems to be a bit too much. So our elbow analysis predicted that a K of 3 was optimal. And when we're visualizing the results, we can confirm that yes, K equals 3 is optimal. So what does this look like in R? So in my R file, I'm going to first set my seed to exclude any impacts from randomizations. And then I'm going to say I want to look at my Ks from 1 through 10. So I'm going to set my K max to 10. I'm going to calculate my elbow analysis based on the within sum of squares and the totals here. So I'm going to call my data frame within sum of squares. And I'm going to tell it from 1 through K max, which is 10, apply the following function to K. I'm going to use my kMeans for my iris2 dataset, columns 3 and 4. And I'm looking for my K. So I'm plotting my K, and I'm going to start at 20, and I'm going to set my maximum iterations to 20 on the total within sum of squares. And then I'm going to plot my within sum of squares. And that's what we're seeing here. We're seeing that for K equaling 1, my within sum of squares is 550.89, and we're seeing that for K equal to 10, my within sum of squares is 5.55. So there really is a significant slope, but we can't quite tell where the elbow is. So let's plot that. And as we're seeing here with our plot, our elbow is at 3 because from here we're seeing an almost linear slope. So yes, my elbow analysis tells me that the optimal number of clusters for my IRIS2 dataset is in fact 3. Even if PAM-K discovers only 2 nicely separated clusters, and even though both my K-medoids and my K-means function kind of mix clusters together, especially our versicolor and our virginica.